Stoichiometry is a specter hanging over the heads of first-year chemistry students. And I think when you look at things in the small picture, you don't realize what it's for. But in the big picture, stoichiometry is really the basis for all quantitative laboratory chemistry. And we need to look at that in applied settings. So I'm going to do a bunch of stoichiometry calculation videos, and we'll work our way up from simple stuff to far more complicated stuff, so you can see these different applications. For right now, I think we need to take a look at stoichiometry in terms of cooking, since that's something most people understand. Before you can cook something, generally you need a recipe, and when you go to use that recipe, you need to figure out what you have, take an inventory of what's available, and then you double check that against the recipe to see what you need. And maybe you'll find out how much extra you have of something, right? And then the main goal when you're looking at it is like, how much can you make? How much do you need to make? And then how much did you actually make, right? Like a classic scenario is making cookies, and like I'll eat the dough, so maybe the recipe's good for like 2 dozen cookies, and then I'll make like 3 cookies because I ate the dough along the way. So that's what we're going to look at in a chemistry context. I'm going to take these first couple problems super slow so we can see the individual pieces. And then in later problems and in later videos, we're going to have to speed up a bunch. I'm going to try and keep track of things right there. I've got 18 examples I wrote out, and I'm hoping to break that down into 9 or 10 videos, just so it's not overwhelming. And again, we're going to start with the very, very straightforward stuff, baby steps, and then we'll work our way up to more complicated looking problems, even though they're all the same at their root, right? So when we're talking about a recipe, we're talking about a balanced chemical equation, right? And when we're finding out what we have, that's our givens. And what we need, we are comparing our given amounts to each other, right? The reactants. And how much extra, we might be looking for some amount excess. Then how much can you make theoretically? That's our theoretical yield. And then how much did you make? That would be some actual yield. And I want to start with this basic idea, because these things are basically the only things that can ever be asked in a stoichiometry problem is for this. And like in the big picture, you'd start with reactants and you'd start with some given amounts, and you had to complete and balance a chemical equation. So I'll skim through that step. We did it in a bunch of other videos. And then we're going to focus on big time this right here and this right here, so that we can do this other stuff. But if we can do this step, everything else is very, very, very straightforward. But again, the key is we've got to have that recipe. We've got to have that balanced chemical equation. And so let's start with one of those. And we'll just say, like, the phrasing on these varies so much. And like, I kind of cheat because I've read them so long, and the students in my class hear me say all the time, like, when you look at a word problem, ignore the words and just look for the numbers. You know, I joke that I can't read because it gives them an idea that I just look for numbers. It's like the Matrix. That's all I see. So we're going to just say that we have like silver, and maybe we're going to react this is heated in some presence of sulfur. And then we'll say given maybe like 50 grams of silver and maybe 10 grams of sulfur. And we're going to ask for this stuff, a completed balanced chemical equation, this step right here, this what do you need and what do you have, and then we'll come up with these other things. So I'm not even going to ask those right now. For this problem, we're going to do everything. In fact, for every problem, we're kind of going to do everything, because if you lay out this general format, it's going to work every single time. And I think that's one of the huge things that's missing in the way stoichiometry is traditionally taught. So we're going to rely on some of the skills that we have worked on previously, like completing and balancing. In this case, you've got silver, right? And maybe sulfur. And we're going to react to yield. And so like this is a synthesis problem. We need to come up with what you can make. Well, the answer is you got to stick them together, and then you got to crisscross and reduce to figure out what your products are going to be. Silver's a 1+, sulfur's a 2-, so we will need 2 of those, and we'll declare that it's a solid. We'll sneak in some balancing work over here. We've got silver and sulfur, 1 and 1. Product side, I've got 2 and 1. So to fix that, we'll need a 2 right there. And that looks pretty good. Now I'm going to sneak in some other very, 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 very important information. and that is the molar masses for these things. And so like from the periodic table, you can see silver is a 107.87 grams per mole, all right, from the periodic table. Sulfur is a 3207. And again, that's from the periodic table. And then this silver sulfide, I'll sneak in the work over here. And for the future problems, I probably won't, because it's the general idea. You're calculating a molar mass. But like silver, you got two of those at 107.87. And then sulfur, you got one of those at 32.07. And then you add those up, and you end up with 247.81 grams per mole. So that's another number we need there, 247.81 grams per mole. And that's good preliminary work. You don't always need it, but it certainly can't help in the big picture. And I realize that's kind of a mess, but we'll take care of that as the problem progresses. So we have a recipe. It is, in fact, right here. Okay. So now we move on to our next step, which is what do you have? We have 50 grams and 10 grams. And if you remember our stoichiometry definition, quantitative analysis of chemical reactions using coefficients to give mole ratios or atom ratios, but I'll just say mole. That's not moles, that's not moles. We need to get moles. So another pre-existing skill we're going to need to utilize is turning grams into moles. And if you remember, you're just dividing by molar mass. We can show that as dimensional analysis, or we can show that just like dividing. So we'll wave our hands at this, and we've got 50 grams of silver, and we've got 10 grams of sulfur. We will divide by molar mass, as I said. We've got them up here as a little note to ourselves, 107.87 grams per mole and 32.07 grams per mole. Again, we need to get moles because that is what the ratios in our balanced chemical equation give us. And these numbers happen to be 0.464 moles of silver and 0.312 moles of sulfur. So the math is there, all right? Here is a major step, and I know this sounds dumb over and over and over. I will declare, and I will label this every single time as what we have, okay? Because we're going to use that have to find what we need. So this supercritical information, and we're going to use that supercritical information to find out what we need. And I realize my space budgeting here is subpar, but we will live with that. So what do you have and what do you need? This is super critical. And set it up this way. I can't emphasize enough. The first box is what is given. Everything after the first box comes from our balanced chemical equation. In this case, I have moles of silver here. I'll need to see moles of silver here. And we've got a 2-to-1 ratio here. So 2 moles of silver for every, I want to know about the other reactant, okay? And so our other reactant is the sulfur, 1 mole of sulfur. And once again in slow-mo, there's a 2 right there, and there's a 1 right there, and there's a 2 right there, and there's a 1 right there. So we find out we need 0.232 moles of sulfur, all right? So moles of silver canceled out, and we end up with moles of sulfur. In this one, I have moles of sulfur in the numerator, 1 mole of sulfur, 2 moles of silver. So we double that, and we get 0.624, moles of silver that we need. We have these amounts, and we need these amounts, and as I said in some previous videos, this to me is a critical step. It seems trivial and it seems kind of elementary, but this is what really determines visually how we're showing somebody what we did. This is what we have, it came from here, this is what we need, and we're comparing it to this stuff. And we're comparing our moles of silver to our moles of silver, and our moles of sulfur to our moles of sulfur. And in this case, we have 0.464 moles of silver, and in order to use all of that silver, we would need 0.232 moles of sulfur. I have 0.312, which means I have extra sulfur, and so we can identify some things here. This silver I don't have enough of. That is going to be my limiting reactant. And then this sulfur I have too much of. That's going to be my excess reactant. All right. It's interesting to note that the one I had more of by mass ended up being my limiting reactant, okay? So don't assume by mass that one is going to be limiting or excess, because we're worried about a mole ratio versus a mass ratio, and silver has a much higher molar mass, so we're going to end up with a proportionally lower number. So as a quick reminder of our definitions here, we have the limiting reactant. And that is the reactant present in stoichiometrically lesser amount, right? The reactant present in stoichiometrically lesser amount. And then the somewhat important part of that, and by somewhat I mean the most important part of that, it determines how much product can be formed. All right, it determines how much product could form. So we're super dependent on finding our limiting reactant. The good news is we did. And then we've got our excess reactant. And fundamentally, that's the one you have too much of, but using our terminology, it's the reactant present in stoichiometrically greater amount. So blah, 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 present in stoichiometrically greater amount. All right, enough vocabulary. The important part to us, how much can you make? And I guess I will highlight this right here. And this is going to be our limiting reactant that determines that. So let's move on to that step. First step here, compare your reactants to each other to find your limiting reactant, and then we're going to get a theoretical yield. And I'll leave a little room right here for something that will sneak in at the end. But for right now, I have, for our theoretical yield, we have 0.464 moles of silver, right? That limiting reactant is the one that determines how much product we can make, and so that is what I'm going to compare to my products, all right? And if you look at the previous videos, we said basically compare your reactants to each other to find the limiting and excess, compare the limiting reactants to the products to get a theoretical yield, and that's what we're doing here. Again, everything after the first box comes from the balanced chemical equation, all right? So there's 2 moles of silver for every 1 mole of sulfur. And we end up with 0.232 moles of, Ag2, silver sulfide. Sorry about that. Silver sulfide, I'm comparing my reactant to my products to get a theoretical yield, and that's Ag2S. And that's moles. If we can do that, we can do whatever else we need to. But I think it's very practical in a laboratory setting to turn that into a mass. So we would just multiply by the molar mass, and we had the molar mass up here. That was 247.81 grams per mole. And again, we got that by adding up the pieces. So once again, we have moles of silver sulfide. We're going to multiply by the molar mass that we calculated, and that's going to get us some gram amount. And I'll just move this down right here. And that's 57.4 grams of silver sulfide. So that is our theoretical yield, how much we can make either of those numbers there. And let's label that. How much can you make? This is our theoretical yield. Now, what other things could we ask for? We could ask for a percent yield based on how much we actually produced in lab. And we can get an amount excess. So I'm going to put over here some divisions, and let's find some amount excess. And this isn't super critical for these problems, but I'm going to show you why it's super useful in the big picture. Let's get our amount excess. That's how much we have left over, right? And all you have to do is take what you have of that excess, and we're going to subtract what we need of that excess reactant, okay? So we have 0.312 of our sulfur, which is our excess reactant, and we're going to subtract the 0.232 moles of sulfur. And in this particular case, we're going to get 0.080 moles of sulfur excess. And we'll multiply that by molar mass to turn that into grams, and sulfur is 3207. So we'll multiply by 32.07 grams per mole. Again, that came from the periodic table, the 32.07, and we end up with 2.57 grams of sulfur. So this here is our amount excess. And I think it's very, very common for people to skip that step, but you're going to see why it's super useful, and I'll mention why it's doubly useful for me in a minute. This is our amount excess. All right, and so with a little bit more information, we can ask another question, and I was negligent by writing it up there, so let's put it in down here. And that other question would be, if you collected some amount in lab, and I'll put this in brown so it matches our original question. So if you had 45 grams of silver sulfide collected in lab, right? If you could have made 2 dozen cookies, but you only collect 3 cookies, what's your percent yield? All right, and percent yield, as you may recall from a previous video, is supposed to be the actual yield over the theoretical yield times 100, right? We need to turn that into this imaginary thing called a percent. So in this case, this 45 grams is our our actual yield, and it had to come from right there. It had to be given. So we will plug that in. I've got 45 grams. And how much could I have made, right? This 57.4 grams of silver sulfide. And we'll end up with a 78.4% yield. And whether or not that's an okay number depends on the reaction, right? Like some organic reactions, you might get like a 0.1% yield or something, whereas some simple lab, high school lab synthesis reaction, maybe you're expecting 100%, all right? So this is our percent yield. And in future examples, we're going to use that to do a whole bunch of stuff, all right? So this seems like a lot of work, but that's because I talked a lot. The key ideas are going to be identify your limiting and excess by comparing your amount of reactants to each other, get a theoretical yield using the limiting reactant, compare it to your product or products, get an amount excess, and if you need to, get a percent yield. And that's really all the things that you can ask for. And what I want to do now real quickly is mention something that was invaluable to me in writing these example problems, and that is you can check your answer. And we can check the answer using the law of conservation of mass. And I will mention right now, like the traditional way to teach stoichiometry is to take this and turn it into moles of sulfur and turn it into a theoretical yield of your product. And take this and turn it into moles of sulfur and turn it into moles of your product, and compare which one has like a fewer number of moles of your product. And like, I think the whole purpose gets lost in that confusing step. It's almost impossible to conveniently come up with an amount excess, and it becomes really, really hard to check your answer without a whole bunch more writing. And while I realized this was like a mess, like here's what we have, here's what we need. We used the limiting reactant to find a theoretical yield. We used our excess reactant to find an amount excess, and then we used our theoretical yield to find a percent yield. It's all there. And I'm going to do that pretty much every single time, regardless of what's asked. So if we look at the law of conservation of mass, our mass of the reactants has to equal the mass of the products. And so in this particular case, we had 50 plus 10. And I'm going to write out more words here than I really want to, but we had 50 grams of silver and 10 grams of sulfur. So we had 60 grams total. In the end, we only had 57.4 grams and that's not 60, but the catch is we have some stuff left over. So your mass of reactants is your mass of products plus the excess. All right, I realize we went a little off the screen there. Plus your excess. And if you look here, we happen to have listed that, our amount excess, plus 2.57 grams, and we end up with 60 grams equals, 60 grams equals 60 grams, all right? And I realize that you might be saying, like, well, that's 59 point whatever. No, it's 60, good enough, all right? Sounds good. So that's the basics of a stoichiometry problem. This looks like a mess. I'm just going to do a separate video for my next example. And like I said, I've got like 18 examples I want to knock out of increasing complexity or different wording or whatever. And they're all the same. That's like the key idea. Every single problem. Take what you have, get moles, figure out which one's limiting and excess by comparing reactants to each other. Then use your limiting reactant to find out about your products. Use your excess reactant to get an amount excess if you need to get a % yield there, and check it, right? Like I said, that I set up 18 of these problems, and like because I'm incompetent and easily distracted, I think I got like 16 of them wrong. But when I got to this step right here, I figured out they were wrong so I could go back and fix it. All right, so that's going to be key, this every single time, and there is a point to it. Anybody can look at this and know what happened, and then we can use this to come up with anything we need in the much, much, much larger problems.